Hello, everyone. My name is Hadrian. I'm a grad student at UCLA, and today I'm going to be presenting this work. Recently submitted to AppJ and soon to appear in the archive. I worked in the Keck Science group under the supervision of Tuan Do, and this work is about the near-infrared spectral index of Sagittarius A star. So Sagittarius A star, or CJ star for short, is the supermassive black hole at the center of the Milky Way. It is identified as a single point source, in particular in the near infrared, where it's seen as a highly variable source. As you can see, this is a sequence of images taken during a single night, and this red arrow here shows CJ star, which dims spectacularly through the night. The favorite picture for this emission is that it's synchrotron emission from relativistic electrons inside the accretion flow of the black hole, but it is still a puzzle, and we don't quite know what is powering this variability. One of the useful diagnostic tools one can use to help distinguish between the different physical scenarios is the near-infrared spectral index, which is essentially the logarithmic slope of the spectral energy distribution, which can be easily estimated using color. So this raises this following question: what is the near-infrared color or spectral index of Sagittarius A star, and does it vary with brightness? Because the behavior of this spectral index as a function of magnitude can help constrain models of the emission, of the accretion flow, etc. Several studies have tackled this question in the past. When CJ star is relatively bright, they agree on a value that is around -0.5. But when CJ star gets fainter, then there's a disagreement between studies that find that this -0.5 value is still valid, and then studies that find a reddening of the spectral index. So what can we add to this? Well, first, this work improves the dynamic range by a factor of roughly 3, mostly on the bright end of this measurements. Second, we've taken extra care in making very accurate spectral index measurements, and that includes very advanced techniques for the interpolation and confusion correction. And finally, a lot of these studies have tackled the question of color variations in a qualitative manner, and we're doing so, we're bringing quantitative constraints to the spectral index variations. Okay, so I worked with a set of observations taken with the Keck Center Orbits initiative. And the data set consists of 7 nights of imaging data acquired with NERC2 on Keck, alternated between H-band, so the gray images here, which is 1.6 microns, and K-prime band, which is 2.1 microns. The data set includes 2019 May the 13th, which is the brightest flare that was ever observed for CJ star, and this explains the large dynamic flux range. We have a factor of 40 in flux that we can probe. So once we have those beautiful images, it's not an easy path to get to actual spectral index measurements. First, we need to extract the photometry from those images. And then the Keck Center is a crowded field, so oftentimes Sagittarius A star is confused with another star in the field. And we need to correct for this effect because stars are much bluer than CJ star, so this would bias the color measurements. And to correct for this effect, we use advanced star planting simulations, and we obtain corrected light curves. Once we have those corrected light curves, we need to interpolate it because we don't have simultaneous measurements in the 2 bands, and the timescale for variation of CJ star is very short. We're doing so using a fancy technique called multi-output Gaussian processes. And the nice thing about this technique is that first, it allows to predict the uncertainty on the interpolation as well as just a value, and that's for the Gaussian process part. And then the multi-output part is simply saying that we're jointly fitting the 2 light curves instead of fitting them separately. And this allows to incorporate the belief that when CJ star gets brighter in one of the 2 bands, it's also going to get brighter in the other band. So once we have interpolated the light curves, the last thing that remains to do is to correct for extinction, and we're doing so using the color of SO2, which is a bright star that we know the intrinsic color. And in the end, we get those beautiful spectral index measurements. So on the y-axis here, you have the spectral index between H and K-prime band, or equivalently the color. And on the x-axis, you have the measured magnitude in K-prime band. And as you can see, hopefully, it looks like the spectral index is fairly constant throughout this large range of magnitudes. You have increased scatter at the faint end and larger error bars. That's because the measurements are a little bit harder at the faint end. But overall, it looks like the spectral index is fairly constant. But this is mostly qualitative, so how can we do this quantitatively? Well, if we look at the literature, there are three physically motivated pictures that have been proposed. The first one is very simple. It's a constant spectral index, and that can be achieved if you have if you inject at a variable rate some electrons inside the population responsible for the near-infrared emission while keeping the overall energy distribution fixed. So first picture is very simple. Picture number two is that of a spectral index that varies linearly with magnitude. And this can be achieved if the variability in the near-infrared is caused by shifts in the synchrotron cutoff frequency instead. And in which case we get this relation between, so it's a linear relation between the spectral index and the magnitude. And we have this slope parameter psi here. And we can actually make predictions for what psi is if the variability is purely caused by this shift in the cutoff frequency. This paper by Witzel et al. Predicts a slope of 1.23 for the HK prime spectral index, and we can test this prediction. And finally, picture number three is a transition between two states with different spectral indices. And in that model, so when SAGE starts faint, it's the quiescent state, which is supposedly quite red. So a spectral index less than -2, let's say around -3. And on top of this quiescent emission, you have some flares, which are explained by a second mechanism. And the second mechanism would have a bluer spectral index, so a spectral index around -0.5 to recover the value at bright fluxes. And this paper by the gravity collaboration makes a prediction for the median of that quiescent state. They say that it should be around 17.7 magnitude in K prime. So these are three pictures, but we can actually test them using a single model. If we start by this using this linear relation, but keeping the slope parameter psi fixed. If we take the slope to be 0, then we recover the picture number 1 with the constant spectral index. If we fix the slope to be 1.23, then we recover the second picture. To this, we can add a background that will cause deviations from this law. We can either take the background to be very red, and that corresponds to that quiescent state I was talking to you about, and in which case it would deviate toward redder values, so more negative values for the spectral index. We can also test the presence of an unresolved star, which will cause a deviation toward bluer spectral indices as SAGE star gets fainter. And to this, we add some noise because, of course, we have real-life measurements. In the end, we have 4 model parameters: the slope and intercept of this linear relation, and the magnitude and spectral index of the background, which causes the deviations. And using this model, we can make parameterized predictions for what the distribution of spectral indices as a function of magnitude looks like. And we can compare this to observations and then do inference to get constraints on the model parameters. If we do this, we get the following posterior constraints for the slope and intercept of the linear relation. And as you can see, 1.23 is not even on this graph. So picture number 2 is ruled out confidently at more than 5 sigma. On the other hand, psi equals 0, which is this red line up here, is consistent within the uncertainties. In fact, if we fix psi equals 0 and rerun the inference, we find out that this model is preferred by the models of the model selection criteria that we tested, so AIC, BIC, and evidence. So we find that there's no reason to leave the slope as a free parameter. We fix it to psi equals 0, rerun the inference, and look at the other model parameters. In that case, eta is, since we fixed the slope to be 0, eta is going to be the constant spectral index. And we find a value that is unsurprisingly -0.5, which agrees with the rest of the literature. And what's also interesting is this panel over here, which gives the constraints on the background. You can see that there are regions of parameter space that have been carved out. In particular, over here, you can see that if we have a very red background, then this background cannot be too bright. So this gives constraints on the red quiescent state. If we have, if we assume that the spectral index of the background is less than -2, then this background has to be fainter than 18.3 magnitude in K prime. And that's in mild tension with the claim of a red quiescent state at 17.7 magnitude. I'm noting that this claim does not include, was not made due to color measurements, but it's based on the flux distribution of SAGE stars. So there's sort of an inconsistency in this picture. Okay, so to summarize, we have color or spectral index measurements for Sagittarius A star in the near infrared, which uses photometric data from Keck in H and K''. We used advanced techniques to get accurate measurements, including for confusion correction and interpolation. We introduced an empirical model to quantify the spectral index variations with magnitude, and this empirical model covers 3 different physical pictures that have been proposed. And in the end, our results are consistent with a constant spectral index with a value around -0.5 over a large dynamic flux range, a factor roughly 40 in flux. We roll out confidently the model that has a strong linear dependence of the spectral index on magnitude, and we find no evidence for a red quiescent state emerge. So with this, I think this is my time. So I thank you for your attention, and we'll take some